I see you're using the Sklearn library's OMP algorithm with a gram matrix. That's a clever optimization technique. It leverages a pre-computed matrix to significantly speed up calculations. OMP itself is a type of linear regression that identifies the most important features from your data, one at a time. We're tackling a linear regression problem using OMP, which I'll explain in more detail below. We have a matrix of features, x, and a vector of the things we want to predict, y. This is the core question, Vamsi. We are going to explore the effects of using this variation of the OMP algorithm that uses a pre-computed gram matrix. Let's dive in. This is fun. Absolutely. The _orthogonal_mp_gram function needs the gram matrix, which is the matrix product of x transposed and x, xx. This pre-computation is worthwhile only when there are fewer features than data points because the gram matrix will be smaller, making calculations much faster. This is false. Although _orthogonal_mp_gram generally improves speed, it's only faster if the gram matrix computation doesn't take longer than the time saved. Correct. The _gram parameter is all about efficiency. By pre-computing the gram matrix, we reduce many repeated calculations during the OMP process. Incorrect. Both should give the same result. The _gram version is just an optimized way to get there. This question asks you to identify the true statements about using the orthogonalmpgram function in Sklearn, a tool for solving linear regression problems. We'll examine each statement carefully. The coefficients are the numbers that multiply the features in your model to predict the outcome. Think of them as the weights assigned to each feature. How much each one contributes to the final prediction. The question is, does using the orthogonalmpgram function affect these coefficients? The answer, based on the explanation, is no. You obtain the same coefficients whether you use the standard OMP algorithm or the version that uses a pre-computed gram matrix. The gram matrix is simply the result of multiplying the transpose of the design matrix, x, by the design matrix itself, x. It's a matrix of inner products which speeds up the OMP algorithm. Imagine it as a shortcut. Instead of repeatedly doing the same calculations during the OMP process, we do them once to create the gram matrix and then use that for faster calculations. This statement is correct. The orthogonalmpgram function absolutely needs the gram matrix to work efficiently. The gain from this pre-computation is mostly seen when you have more samples than features, a scenario where the gram matrix is smaller than the design matrix X, thus reducing computations substantially. This is also true. Using the gram matrix avoids redundant matrix vector multiplications, making the algorithm much faster. This is the core benefit of the orthogonalmpgram function. This statement is false. It's not always faster. The advantage only appears when the number of features is significantly less than the number of samples. The overhead of creating the gram matrix could make it slower than the standard algorithm if that condition isn't met. This is also false. Both algorithms produce identical coefficients. The orthogonalmpgram function just uses a clever shortcut to reach the same result quicker. I see you're working with orthogonal matching pursuit, a method for finding a small set of features that best explain your data. The gram matrix is a clever way to speed things up. It's essentially a pre-computed summary of how each pair of features relates to each other. We use it to avoid redundant calculations later. This is the core question we are tackling. We're using Sklearn's tool to solve a linear regression problem. That means we're trying to find a line, or hyperplane in higher dimensions, that best fits our data points. We're also using the _gram parameter in orthogonal matching pursuit which tells the algorithm to use that pre-computed gram matrix. We will investigate the effect of using this parameter. This statement is correct. The _orthogonal_mp_gram function needs that gram matrix, x, t at x, computed ahead of time. Multiplying the transpose of the design matrix X by the original X gives us the gram matrix. It is beneficial only when the number of features is much less than the number of samples. Think of it like this: if you have many fewer features than observations, pre-computing that gram matrix saves a lot of time later. This statement is incorrect. While pre-computing the gram matrix usually speeds things up, it could also be slower if the number of features is very large compared to the number of samples. The computation of gram matrix takes time. So, it does not always mean faster computation. This is also correct. The whole point of using the gram parameter is to avoid repeating calculations, thereby reducing the computation time. It's a computational shortcut. This is incorrect. Both methods use the same underlying algorithm. They just differ in how efficiently they perform the same calculations. They should produce the same solution, coefficients, not different ones. I see our data. The design matrix X has 100 samples and 50 features. The target vector Y has 100 values which correspond to each sample in X. This represents the gram matrix, obtained by multiplying the transpose of matrix X by matrix X itself. It's a 50 by 50 matrix. In simple terms, this matrix summarizes all the relationships between the 50 features in our dataset. I see, you're referring to a specific optimization of the orthogonal matching pursuit algorithm. OMP is a method to find a sparse solution to a linear regression problem. Sparse means we're looking for a solution using only a few of the available variables. The gram matrix is a way to speed things up. It's a matrix formed by multiplying the transpose of the design matrix by itself, XX. By pre-computing this, we avoid redundant calculations later. This question focuses on the orthogonal_mp_gram function in the scikit-learn library, a popular Python library for machine learning. It asks about the implications of using the gram matrix in OMP for linear regression. I can help you break down the different aspects of this function, like when it's advantageous and its computational cost. Yes. orthogonal_mp_gram needs the gram matrix, XX, calculated beforehand. This is like doing some prep work before starting the main problem solving. It is only beneficial if the number of features, columns of X, is much smaller than the number of samples, rows of X. The fewer features there are, the smaller the gram matrix and the bigger the advantage of the pre-computation. This statement is false. While using the gram matrix often speeds things up, it's not always faster. The time it takes to initially compute the gram matrix needs to be considered. If you have far more features than samples, the gram matrix will be large, and the time spent calculating it outweighs the time saved by not calculating the matrix vector products. Exactly. The gram parameter, by providing the pre-computed gram matrix, cleverly avoids many repeated calculations normally found in the standard OMP algorithm. These calculations involve multiplying matrices and vectors, which can be computationally expensive. This is incorrect. The solution remains the same, only the method to arrive at that solution is different, and potentially faster. orthogonal_mp_gram uses the same underlying algorithm as the standard OMP, just with a computational shortcut. This describes your input data. It's a matrix with 100 rows, samples or data points, and 50 columns, features or variables. This is the vector that you are trying to predict or approximate. There's 100 values here, one for each of the 100 samples in the design matrix. Here, X represents the transpose of matrix X, rows become columns and vice versa. The expression, X at X, denotes the matrix multiplication of the transpose of X by X itself, resulting in the gram matrix. This matrix contains the inner products of all column pairs of your design matrix X. This is the outcome of using the optimized OMP algorithm, orthogonal_mp_gram. It's the set of coefficients that best approximates your target vector Y using a subset of features, a sparse solution, obtained using the gram matrix to improve efficiency. I see OMP as a clever algorithm that finds the most important features in your data to explain your target variable. It's like a detective meticulously selecting clues to solve a case. The gram matrix is a shortcut, a pre-calculated summary of how the features relate to each other. This can speed up the detective work significantly. This question tests your understanding of how this shortcut affects OMP's speed and accuracy. We'll analyze the given options to see which statements are correct. The gram parameter refers to using the pre-computed gram matrix. Think of standard OMP as repeatedly doing many small multiplications. Using the gram matrix is like doing one big calculation up front, which is usually more efficient and avoids redundant computations. That's the core of the speedup. I'd say this statement is wrong, because the pre-computation step for the gram matrix can sometimes be slower than the standard OMP if your data has many more samples than features. In short, this shortcut isn't always faster. It depends on the shape of your data. This represents the inner products, dot products, of every pair of columns in your feature matrix. Is the transpose of. Imagine it as a summary of how much each feature is related to every other feature. Pre-computing this helps speed up the OMP algorithm. These are the values that tell you how much each feature contributes to your prediction. Crucially, using the gram matrix shortcut shouldn't change these values. It only changes how quickly we get to the same answer. This refers to calculating the gram matrix before starting the main OMP algorithm. It's like doing some prep work before starting a project, which might save time later. In this context, calculating the gram matrix beforehand saves many calculations during the OMP algorithm itself. This is the core orthogonal matching pursuit algorithm itself. It's a method for finding a sparse solution to a linear regression problem. In simpler terms, it figures out which features matter most in explaining the target variable. The output of the OMP algorithm. It shows the weight or importance that OMP assigns to each of the features used in the final sparse model. I see that you're referring to a specific method for solving linear regression problems. It's a variation of the orthogonal matching pursuit, OMP, algorithm. OMP is a powerful technique for finding a sparse solution, that is, finding the smallest subset of features that best explains the data. Adding, with gram matrix, indicates we're using a clever trick to speed things up, as I will explain further down. Okay, the question focuses on _orthogonal_MP_gram_, a function in the scikit-learn library. This is a specific implementation of OMP that uses a pre-computed gram matrix to improve efficiency. We'll investigate the benefits and trade-offs of using the gram matrix in this context. This is the key function, a variation of the standard OMP algorithm. The gram part signifies that it leverages a pre-calculated gram matrix, explained below, for faster calculations. Think of it as a shortcut that makes the whole process quicker. This is where the magic happens. The algorithm's output, the coefficients, numbers multiplying each feature, that together provide the best sparse solution. The key here is that whether you use the standard OMP or orthogonal_MP_gram, I expect to see the same solution, assuming no numerical errors. The same solution, even with different approaches. The gram matrix is a special matrix derived from our data matrix, X. It represents the inner products, dot products, of all pairs of columns in X. Calculating it beforehand allows _orthogonal_MP_gram to avoid repeating a lot of those calculations during the main OMP algorithm. In simpler terms, a smart way to save computation time. That's absolutely right. This statement highlights the core idea. _orthogonal_MP_gram is all about pre-computing the gram matrix. This is only really beneficial when we have far fewer features than samples. Think many more rows than columns in your data. Correct. Using the gram matrix means we do fewer calculations. Instead of many repeated calculations of dot products within the OMP algorithm, it uses the gram matrix's pre-calculated values. This is like having a cheat sheet ready before the exam. This is false. While _orthogonal_MP_gram can be faster, it's not guaranteed. The speed advantage depends on the data's structure. number of features versus samples. The initial gram matrix calculation can take time, potentially making it slower than standard OMP if we have many features. This is incorrect. Both algorithms use the same underlying OMP procedure, just one is optimized by using the gram matrix. Thus, they should provide the same solution, within numerical tolerance, of course. I'm tackling a linear regression problem using scikit-learn's OMP algorithm, specifically orthogonalmpgram. I have a design matrix X, 100 rows, 50 columns, and a target vector Y, 100 values. I'm using the GRAM parameter to potentially speed things up. The question is about how using the GRAM matrix affects the computation in the result. I'm working with a design matrix X, which is a 100 by 50 matrix 100 data points with 50 features each. My target vector Y has 100 corresponding values, one for each data point in X. This is a variant of the orthogonal matching pursuit, OMP, algorithm that uses a pre-computed gram matrix. The gram matrix is a way to optimize computations. I'll explain it in detail later. The gram matrix, calculated as X, the transpose of X multiplied by X, contains all the inner products of the columns of X. Pre-computing this matrix helps speed up orthogonalmpgram because I don't need to repeat these calculations during the algorithm. The standard orthogonal matching pursuit, OMP, algorithm is a greedy method for finding a sparse representation of data. Think of it as iteratively picking the most important features to explain the data. In standard OMP, the algorithm involves many repeated matrix vector multiplications. These are computationally expensive, especially with large matrices. The GRAM matrix approach helps avoid this. This is the core concept. OMP, or orthogonal matching pursuit, is an algorithm for finding the best way to represent data using only a few of its features. Think of it as a smart way to simplify complex data. Using the gram matrix, X, speeds up the calculation because instead of calculating many repeated values, you already have them calculated once. It's a clever optimization.